Hi students, this is lecture 6. We are going to discuss some statistical distribution. We already visited some statistical distributions in the tutorials before, but in this lecture we will discuss them again. Statistical distributions and its importance to network simulation. Simulation engineers use simulators to study the behaviors and correctness of systems by observing the output information generated by a simulator, giving its input specifications. In such cases, a crucial task in developing simulation is to determine the complete input to the simulator. In order to achieve this, one often must make random choices. For example, in communication system, node A and node B communicate exactly once every t seconds, where t is determined by choosing a random number in the range of 0 and 10. This is an example of a statistical distribution, which is a formal means of specifying the relative likelihood of different system inputs. I mean by this that the t seconds is not determined, is or indefinite, but to understand how to put the value of t in a computer simulator or in a network simulator program, we have to use a statistical distribution, which are based on mathematical models. An introduction to statistical distributions. A continuous random number variable is a variable that takes random values over a continuous set of possibilities. A discrete random number is a variable that takes random values or a finite or countably infinite set of possibilities. The height of a randomly selected human being is an example of continuous random variable, because there's no exact numbers of, like, for example, millimeters, centimeters. People can be measured differently. Okay. The year of birth of a randomly selected human being is an example of discrete random variable, because we all know the birth year or birthday is a fixed number, so these are discrete. It's obvious. We already discussed what's the difference between a continuous random number and discrete random number before. Probability density functions. This is a review for some probability measures. Okay, let x be a continuous random variable on an interval between a and b. The probability of x that lies in the interval a and b can be expressed by the following function: probability of probability of x between a and b is equal. This is the continuous random variable, is equal to the area under the curve of f of x between limits a and b. Then the function f of x is called probability density function PDF of the random variable. A PDF satisfies the following conditions. You all know that there are three conditions that satisfy the PDF or probability density functions. F of x is greater than 0 for all x in a and b. That's interesting. It means that between a and b, the function f of x has to have a value greater than 0. There's no negative number, and it can be equal to 0, but it has to be more than 0, positive, plus 0. The second condition is the area, the whole area of f of x must be equated to 1 or equal to 1. Also, f of x should be 0 if x is not in a and b. So beyond these limits, there should be no f of x at all. These three conditions make the PDF satisfiable. Now we can discuss cumulative density functions as well. The cumulative density function CDF measures the probability that a number variable x assumes a value less than or equal to a specific value. By convention, if the PDF is denoted by f of x, notice that f is small here, then the CDF is denoted by f capital of x. Unlike the PDF, the CDF is able to quantify both discrete and continuous random variables. The CDF for a discrete random variable x is f capital of x summation of probability per xi. This is the main differences between CDF and PDF. PDF always in continuous random variable, while CDF can be combinated on can be expressed in discrete or continuous. The cumulative density function measures the probability that a random variable x assumes a value less than or equal to the specific value. By convention, if the PDF is denoted by x, this is repeated. Okay, this is the law of discrete value of CDF. This is the law of the continuous value. Okay, the CDF of a function f of x. The function f capital X has the following properties. Since PDF has its own property, CDF has also another set of 3 properties. F is an increasing function. It means that if A is less than B, then f of A must be less than or equal to f of B. It's an increasing function because it's cumulative. Okay. Limit x of plus infinity equal to 1. Limit of x as goes to approach to negative infinity has to be equal to 0. Okay. Suppose now we are going to discuss joint and marginal distributions. Suppose there are 2 random variables x and y which might have the same or different probability distributions. If x and y are random variables, then x and y together is also a random variable, taking values in the Cartesian of the spaces from which x and y are drawn. The distribution of the random variable jointly x and y is called the joint distribution of x and y, and is denoted by between brackets x, circular brackets x and y. Distributions of x and y are each referred to as marginal distributions. For example, suppose we have 2 fair dice, or 2 fair dice, a red one and a green one. The role of the red die is the variable x1, while the variable x2 represents the value of the roll of the green die. We record the output x1, x2 after each row of the pair and define x equal to x1 plus x2 and y equal x1 minus x2. The probability distribution of x1 is called a joint distribution, and the probability distribution of x and y is called marginal distribution. I think this is easy to understand. It's better to see example to be more explainable. Okay, now we have 2 important terms, correlation and covariance. They are very important. Covariance of a random variable x and y measures the relation between x and y. This is covariance. Intuitively, when x and y are independent on one another, the covariance gives a score around 0. But if the variables are dependent, then their covariance is high. This is also important. The covariance is important. It's computed as, this is the equation, mathematical expression of covariance between x and y. Okay, it's the summation of all elements in x and all elements in y, such that the summation of subtraction between x, this is the mean value of x, mean value of y, divided by the number of total values. The correlation measures the strength of the linear dependence between x and y. The values of the correlation function are in the range between -1 and 1, always. Don't forget that. The formula to calculate the correlation is we have to first calculate covariance of x, y, then we can compute correlation. Correlation looks at the covariance of x and y divided by standard deviation of x multiplied by the standard deviation of y. The standard deviation is summation x to the square root to square actually under the square root of this value. This is the standard deviation. Okay. Discrete versus the continuous distributions. Continuous distribution describes the distribution of continuous random variables. Probability distribution is continuous if its CDF is continuous. For example, we can consider the probability distribution of the time we spend waiting for the bus each morning. If the bus arrives at every 20 minutes, starting at 6 a.m. until 8 a.m., and if we arrive at the bus stop at a random time in this 2-hour interval, then the probability that we wait a period of time t has a continuous distribution, since t is a continuous variable. While discrete distribution describe the continuous distributions, which are zero on all but a finite or countably infinite set of values. A probability distribution is a discrete if its CDF increases in quantized steps. The Bernoulli and binomial distributions are examples of discrete distributions. They are countable. As an example of a discrete distribution, consider a game of chance in which we pick numbers from the set 1 to 5. The number of possible values in this case is finite. Because we know if you draw any of the numbers, it is finite because it's either 1, 2, 3, or 4, or 5. Therefore, the game gives rise to a discrete random variable. The value of the number selected on the distribution of this random variable is a discrete distribution. This is the main difference between discrete and continuous distribution, not random variables. We discussed previously random variables. Now we are discussing distribution. It's the same definition. We have indefinite number of undefinite value of the number here, while here in the discrete valuation we have set of finite numbers. Now let's talk about discrete distribution. Discrete distribution describes the statistical distribution of the discrete random variables. In the following, we discussed 4 discrete distributions, which are the Bernoulli, binomial, we skip that, geometric distribution, and Poisson distribution. Bernoulli distribution. Bernoulli distribution is discrete probability distribution for a Bernoulli trial. A random experiment that has only 2 outcomes, usually called a success or a failure. For example, the probability of getting a success while flipping a coin is 0.5. The probability of a failure is 1 minus p, which is also 0.5. Okay, it's a special case of binomial distribution for n equal 1. In other words, it's a binomial distribution with a single coin. So this is the main difference between binomial distribution and Bernoulli distribution. Bernoulli distribution is a special case of binomial distribution, but for the number of items, the number of trials, single trials is equal to 1. Okay, this is the example of Bernoulli distribution for 0.6 and 4.4 as well. Okay, the probability of the failure is labeled in the x-axis as 0, and success is labeled as 1 in the following Bernoulli distribution. The probability density function PDF for this distribution is discrete. You remember the PDF is not discrete, is what? It's continuous. So it's going to be equal probability to the power of x multiplied by inverse probability to the power of 1 minus x, which can be also written as this formula. Now let's go to the geometric distribution. The geometric distribution is a discrete distribution defined by the probability of getting a run of consecutive successes in a Bernoulli experiment followed by a failure. For example, a sequence of n heads followed by a tail. Okay, the probability of a random variable x that has a geometric distribution is this represented by this formula: probability of x theta multiplied by y minus theta to the power of x minus 1. for x equal to 1, 2, 3 for discrete. As an example of geometric distribution, consider our game of flipping a coin as well. Using the geometric distribution, we can calculate the probability of getting a run of x heads, followed by a single tail in the game. Okay. Now let's jump to Poisson distribution. The Poisson distribution was developed by the French mathematician Simon Denis Poisson in 1835. The Poisson random variable satisfies the following conditions. There are three conditions for Poisson random variable. The number of successes in two disjoint time intervals is independent. So if the time is not the same, then the number of successes is independent. It means that if today is sunny, it doesn't mean that tomorrow will be sunny as well. Okay. The probability of a success during a small time interval is proportional to the entire length of the time interval. Apart from the disjoint time intervals, the Poisson random variable also applies to disjoint regions of space. So for the second condition, the probability of a success during a small time interval is proportional to the entire length of the time interval. For example, if you find the probability for a week interval, it can be proportional to the entire month or entire year. Okay, this is good conditional Poisson. This condition for the Poisson random variable. Apart from disjoint time intervals, the Poisson random variable also applies to disjoint regions of space. This is advanced method. You don't have to understand it. It's not always about the time. It's also about the space of items. Okay. We have too many applications of Poisson distribution. The number of deaths by a horse kicking in a Peruvian army, first application. Birth defects and genetic mutations for rare diseases like leukemia, but not AIDS, because it is infectious and so not independent. Especially in legal cases, car accidents, traffic flow, and ideal gap distance, number of typing errors on a page, hairs found in McDonald's hamburgers, spread of an endangered animal in Africa, failure of a machine in 1 month. Those all are examples of Poisson distribution. The probability distribution of a Poisson random variable is represented by the following formula. You are familiar with because we already studied in the tutorial number 4 or 5.